Where, for example, you mentioned in the anthropic principle that you'd like to predict probability distributions. Where are those probability distributions going to come from?
Yeah.
Right? Who's going to set the probabilities? Here, we have a fundamental part of the theory that sets the probabilities for all the possible histories, and therefore, if the constants vary in those histories, sets the probabilities for what constants. Now, there's a little caveat here, right? We have to talk about observations, and that's where observations, there's a distinction between predicting probabilities for what occurs and probabilities for what we observe. Probabilities for what we observe are conditioned on our observational situation.
First-person probabilities.
Yeah, they're first-person probabilities. So, for example, take the microwave background temperature. So here we have a theory of the wave function, and we have a theory of the Hamiltonian. What does it predict for the temperature of the microwave that we background radiation that we observe? That's a meaningless question, because
need the time.
The microwave background is changing in time. It will predict the history of the microwave background, but it won't predict what we observe because it doesn't describe how we're set up to do the observation. Everything is inside, remember, the observers, the apparatus, and so forth. So we're predicting a correlation between a description of the apparatus and a particular time and the temperature.
But you could use the Dickey argument to specify a particular time, I suppose.
The Dickey argument would come in, right, as a kind of selection effect, right, if you like, on predicting that we have stars. So some histories, let's review again the story about the origin of large-scale structure. How do we have stars? Well, quantum fluctuations in the beginning, which occur inevitably, right, even if the initial thing is very smooth, grow under the action of gravitational attraction to predict these systems. Some histories won't have stars because just by chance the fluctuations didn't grow or they weren't of the right size. So it would select, if you like, right, by requiring that it be consistent with our observational situation to have stars. That's how we would... Or put it differently, what you call anthropic reasoning is automatic.
Is automatic.
It's not a principle, it's not an assumption, and it doesn't change the objective character of the theory of the state. And so that's a big improvement.
So as I understand it, you make this distinction between the third-person description of the universe, which is what comes out of the equations of the physics, and the first-person description, which is simply saying there is a selection effect. We have to condition our observations on the fact that we are here in order to make the observations. So it's what I find. I mean, I think this is. I'm quoting your paper on the. I think entitled "The Observer Strikes Back," where you make this crucial point that you necessarily have to bring in the first-person perspective to describe the universe we actually see.
To predict observations.
To predict observations.
It's a trivial remark. If we have
how many? Because I mean, when I spoke about fine-tunings, I went through a huge number of constants. Which are the ones you mainly look at? You're looking at what I sometimes call Q, the amplitude of the fluctuations, which you just referred to. I know you also refer to the cosmological constant, because I know in your paper you talk primarily about Q and about lambda, and you point out, through the Weinberg argument and things like that, you are naturally confined to a small range of parameters for lambda and Q, and you have some very nice arguments there for what the relative values of Q and lambda. I mean, maybe you'd like to say just a little bit about why your approach is very successful in actually predicting the relative values of Q and lambda.
I'd like to come back to that in a second. I want to finish up our previous topic, which is the difference between first and third, with a little example. Because what's most probable to be observed is not necessarily what's most probable to occur.
Yes.
And a very simple event is just the existence of fluctuations in the universe. The most probable universe will have no fluctuations.
Yes.
Right? Because fluctuations cost action in this framework.
Very little
They lower
inflation.
the probability. Right?
Very little inflation.
Very little inflation, et cetera. There's a whole stream of those things. But obviously, we are a fluctuation. right, in the universe, a very special one. Well, at least we think we're special. I'm not sure whether the universe thinks we're special, but and therefore the most probable thing for us to observe will not be the most probable thing to occur, which is no fluctuations.
Indeed.
Right. Yeah. So we, in fact, that's the way we predict the fluctuations. So that's another important thing, because that's why anthropic reasoning is automatic, because we've already have the observing system in there to predict what the observing system observes. It's almost a complete tautology. Now let me come back to the one specific case we did. The inspiring part about your talk is all the other examples of fine-tuning to which this could conceivably be applied. But we only did one case.
Exactly. I was interested in how you put all these other fine-tunings into your analysis of Q and lambda.
We didn't, well, we assumed a lot,
yeah.
right? Which things that were fine-tuned, like the age, for example, which is the Dickey argument. But we had, there's a long history of anthropic discussion, and particularly the work of Tegmark, Rees, Wilczek, and Weinberg, and all that, based on assuming that identifying an anthropically allowed range of the constants, saying we have to be in there someplace, and then just assuming a uniform distribution over that, and then arguing what that would predict for the constants. That worked very well for Weinberg, right? But as Livio, Rees, and other people showed, it doesn't work if you let the amplitude of the primordial density fluctuations, called Q, right, when they leave their horizon, also scan. That is, the ripples in the microwave background.
Two-dimensional plot of Q and lambda.
Two-dimensional, right. So, but we have the probabilities from the wave function of the universe, right, to fill in that plot. And as I've just mentioned, fluctuations tend to be suppressed. They have lower probabilities. So the no boundary wave function predicts what in traditional anthropic reasoning would be called a prior, assumed uniform, to be something which sharply favors lower values of Q. So in fact, it favors the lowest value of Q.
10 to minus 5 or something.
It's consistent with the present age, which, as you remember from the history of the fluctuations, people were trying to measure the fluctuations, and they kept not finding them at various levels. And they said, well, if we get down to 10 to the minus 5, there's going to have to be a major revision of the theory if we don't find any. But they did find them at 10 to the minus 5. So that's consistent with this story, and it restores Weinberg's original anthropic.
So just to summarize, if I've got this correct, Weinberg originally had this nice argument for the value of lambda.
Assuming a uniform distribution.
Assuming just lambda. When you put in Q, the fluctuation amplitude as well, it no longer works so beautifully because we're quite a long way off from the phase of values of Q and lambda. When you marry it up with the idea of the no boundary proposal, you're saying you naturally find we are in the sort of reserve value, or the small value of Q.
Is that an accident? We only did one case, but it worked out, right? So the interesting thing is to expand the number of cases.
Right? You could have put the photon to baryon ratio and make it.
Well, precisely, right? So we need somebody like you to help us with this, right? Frankly, right? So that's the idea that we should not. If the theory consists of two parts, and you want to make an argument for what tunings you have, you should put in both parts, or whatever your best theory is. And furthermore, if it's confirmed, that's evidence for this theory.
Can I now put your discussion in a broader context? Because I sort of see quantum cosmology as being one particular version of the multiverse, which works very nicely in the ways you describe. But there are other multiverse scenarios. And for example, there is the string landscape scenario, there is the internal inflation scenario, there's the brain cosmology scenario, there's even the bouncing universe, cyclic universe scenario. And so what I wanted to ask you was, are all these different scenarios, are they also compatible with the quantum cosmology? I mean, when in your paper, on quantum cosmology in the observer bounce back, for example, you make explicit reference to the string landscape scenario. So do you see that, and indeed the eternal inflation scenario? So in some sense, you're saying that these different multiverse scenarios, and we've got three, we've got quantum cosmology, we've got the string landscape, and we've got the eternal inflation. You're saying in some sense, because you actually do invoke those, and you invoke those other two scenarios when you do your calculation. You invoke inflation and you invoke string landscape. So do you see all of these different multiverse scenarios as in some sense all being connected? So one shouldn't just think quantum cosmology is one version, string landscape's another version, eternal inflation is another version. In some sense, you see them all coming together.
Depends on what you mean by connected, right? But they are connected in the following sense, right? That is, all those different theories, the multiverse, correspond to different theories of dynamics. String theory, or a simple potential that allows for bubble formation, or even a simple potential that for the matter fields that just have many minima corresponding to many different cosmological constants. So they're connected in the sense that they all fit into a common framework, and even with the no-boundary wave function, which differs in form from one, but in variations of the dynamical theory. So if it's string theory, then we'll get to the string landscape. If it's some kind of model, as we did in our latest paper, that leads to the formation of bubbles of false vacuum, just taking a simple model, then we will get that no-boundary predictions for that, which are exactly the same as we argued for Coleman-DeLucia. So if the framework puts them all together, but the specifics of the framework differ from one landscape to another.
What about the cyclic scenario? Because that's one of the oldest multiverse scenarios where you recycle the constants at every big crunch. But am I right in saying, does the no-boundary proposal allow you to have a cyclic model? In other words, say there was a universe before the Big Bang, or does the no-boundary proposal basically said our universe began out of this state?
That's an interesting question, right? The one thing it doesn't allow is a universe that goes through a bounce classically, right? So, for example, we examine the case of bouncing universes, simple models where we just have a cosmological constant, and then that's de Sitter space, which comes down, bounces. In the intermediate region, we find that the classical story, quantum mechanics, as I've just, classical physics is an approximation to quantum mechanics, as I've just, and it doesn't necessarily hold everywhere. So you have to check where are the probabilities high for classical correlations and high. We essentially use WKB, so at a bounce, the universe won't be classical, but there will be quantum transitions from one side to the other. And we can calculate what those quantum transitions are, again, in a fairly crude way, but so the universe collapses homogeneously and isotropically, it gets down, and it can come out with a different set of parameters.
Essentially, you are allowed to have a cyclic model as well. So.
Well, in that sense, yes, I think so. Now, the recollapse is a harder question to analyze, but it's conceivable that you could have some kind of quantum transition to go on. You will need it, right? Because, of course, the cyclic model has to do something to get rid of the inevitable singularity in the big crunch. Of course, Roger has some theories that the matter will become conformally invariant, and therefore we won't need to worry about that. But.
So that's good news then, because now you've made a link with cyclic cosmology. What about the final one? I talked about brane cosmology. Now, I know when you do quantum cosmology, you normally do it in the context of ordinary 3+4 dimensions. But it's always seemed to me that if you're going to invoke string theory type arguments anyway, why not accept the fact that when you go back towards the quantum cosmology epoch, that you might first reach a higher dimensional epoch? In other words, before you get to I mean, quantum cosmology is something that happens at the Planck time, but it's quite conceivable that before you get to the Planck time, you go through a higher dimensional regime where the universe has got extra dimensions. So can I also put brane cosmology, for example, in the context of quantum cosmology?
In my talks, I have been showing a slide of a scorecard for the no boundary wave function. Does it answer this question? Homogeneity and isotropy, yes. Spectrum density fluctuations that we see, yes. The existence of isolated subsystems, which is not a given thing in cosmology. Some information maybe about the constants. Then we have a list of things that we haven't done, right? Among them is number of large and small dimensions or transitions between them, right? But in principle, for example, or the kind of dynamical theories we have, if there's a selection between them, the number of time dimensions, why do we just have one, right? All that, there's some speculative evidence on all that, right, but very weak. We have no calculations have been done because there's not enough time, strength, cash, and patience, right, to have done them. But for the future.
Okay, so in some sense, your approach can embed all of these other approaches, I think, to the multiverse. The quantum cosmology, in some sense, can potentially link to all these different versions.
I think it certainly incorporates a lot of them. I don't want to say all of them because somebody will come in tomorrow with something that doesn't fit, right?
I mean, finally, because I know we're running out of time, but I was very struck with your paper about the Observer Strikes Back, that you have this acronym for the, I always forget it, the IGAS.
Information Gathering and Utilizing System. The point of the acronym was, this was Murray's idea, is observers seem to select humans to many people. So we wanted something that characterized what these systems were doing, and we came up with this word IGAS, which is an acronym for Information Gathering Utilizing System, characterized just by acquiring information, having a model of the universe, tables and chairs in these various places, right, and then a door there, and then acting on the basis of this model. We want to go to lunch, we have to go out through that thing over there. And that's what a large class of systems, for example, a self-driving car.
No, absolutely. And that's what I found interesting about, in some sense it seems to me you face the same problem that I faced when I talked about the complexity principle. You still got to define what you mean by an observer, or in your case, what you mean by an IGAS. And there's still quite a lot of leeway even in your picture. I mean, in your picture, would you have any particular versions if it turned out that you really did need to? You see, the point is, in quantum mechanics, people do argue sometimes that consciousness is what collapsed the wave function. And I know that's not a mainstream view, but it's one particular interpretation of, and indeed, we don't even like the term collapse of the wave function from an Everett point of view. But
it doesn't fit very well in decoherent history.
Indeed. Right, what I was going to ask you was, is there any natural way in which I can put consciousness into your IGAS? In other words, if I say there is a subset of IGASes which have consciousness, is that something you can easily accommodate in your model, or is it something you would be averse?
Well, you said easily accommodate, right? Yeah. We don't know what consciousness is exactly, and so it won't be easy, right? But if it was sufficiently understood, in principle, it's just another, we're just physical systems in the universe, not distinguished, right? Particularly as far as the formulation of quantum mechanics. So quantum mechanics doesn't restrict you to consider non-conscious systems or conscious systems, whatever that might mean. So in principle, of course, we could describe it, right? How easily it is to describe, if it's a physical statement, right? That is, it's translatable into the basic variables of whatever theory we
But you are specifically excluding, I was interested in that, Mark, you specifically excluding a picture where consciousness is invoked to collapse the wave function. You said that's out of the spirit.
I would say we are doing that. I didn't know before talking to you that we were doing that, but I think the answer is yes.
So yes, so that we are it.
We are not dealing with a quantum mechanics that has as a prerequisite, right, understanding consciousness.
I just thought that would be an interesting way of linking up the two ways in which consciousness comes. Consciousness comes in through the anthropic principle, but sometimes it comes in because people have argued that consciousness collapses the wave function, and you would like to keep those as distinct.
We think of the collapse of the wave function as being fairly trivial. It's just the way histories are represented. Subplanes of histories don't have any collapse in them at all. So we get away from
it would happen even without consciousness.
It doesn't even have to happen at all, right? I
Yes.
mean, for this description. We describe everything four-dimensionally, right, in terms of histories.
Yeah.
It doesn't have to, it has to happen in certain situations. It will happen.
So at this point, do we have to stop? Is that what you're nodding?